Okay, so enjoy this, and then I go to my earlier prepared lecture, which is two subjects that I'm supposed to cover in this morning lecture. The first lecture, why is soft matter soft? It is soft matter summer school, so it's appropriate to ask what is soft matter, and in particular, why is it soft? And then, more specifically, closer to polymer physics, why is the ideal polymer ideal? So why is soft matter soft? In order to start this question of why soft matter is soft, let's discuss why hard matter is hard. So hard matter, for instance, this table, this chair or this table is quite hard. You push on it, it does not respond very much. Why is it hard? Why our traditional solid materials are hard? So the way to get a physical feeling for it is to do some estimate. The estimate is here. So when you compress this object like this, what happens? You actually, inside, you push one atom against the other atom. That's what happens inside. And therefore, the way to estimate this bulk modulus, and bulk modulus is essentially energy per unit volume. So how do you estimate it? You take volume, which is the size of this atom, and the size of the atom. By the way, I think this slide, which has some equations written here, known to you from physics textbook, I suspect, I'm not sure, but I suspect that this is the last slide in this summer school that you see Planck constant there. I guarantee that it's the last my slide with Planck constant. I suspect that there will be no other. So you have atom size, which is about 0.1 nanometer. And then when you compress, what happens, you work against the Coulomb energy, which is the energy of interaction between electrons and nuclei. And this is basically this number at the distance of 0.1 nanometer. And then you take this divided by volume, and then you obtain something called the order of 10 to the 7 megapascal. So to compare, it is, well, not very far from the diamond bulk modulus, but it is radically different from this typical soft material. You see many orders of magnitude away. So that means that soft materials are somehow really belong to some different realm. It's a different field. It must be a different field of science to understand such a dramatic difference in magnitude. So just a note on units that are in use and useful in soft matter physics. In molecular words, typical distance. So atom is 0.1 nanometer, DNA width is 2 nanometers. So nanometer, forget about light years, meters, kilometers, miles, all of this is inconvenient. Nanometer is your unit. This is how you should think about it. Natural unit of force is piconewton, and pressure is force divided by area. Piconewton divided by nanometer square, it's megapascal. So megapascal is the natural unit of pressure. And at room temperature, kBT, thermal energy, is 4 piconewton times nanometer. Something that is useful to keep in mind. 4 piconewton, natural units, piconewton times nanometer, 4, convenient number, pleasant, so it's easy. So what else? We decided that soft matter is not pressing things, pressing atoms against one another. What else? The prototypical system that resists your attempts to press on it, and it's not because you push atoms against one another. Prototypical system is ideal gas. I'm not suggesting to you that ideal gas is really soft matter, but it's somewhat soft. So let's talk a little bit about ideal gas. Just as a reminder, I hope everybody knows about ideal gas, but nevertheless, let's talk about ideal gas. So this is ideal gas law, and there are some features of ideal gas law that I want you to realize. First of all, pressure of ideal gas is proportional to temperature. So therefore, pressure, essentially the force by which ideal gas tells you that there is something, there is material inside. This pressure is proportional to temperature. This pressure is entirely due to random motions of random chaotic thermal motions. And soft matter, as you will learn, is all about random chaotic motions of atoms and molecules. This is number one, proportional to temperature. Number two, it's proportional to the number of particles in the system. Proportional to the number of particles simply means that this force is produced by every particle, every atom, or every molecule in the system independently of others. Every atom tells, it's like voting in democratic country. Every citizen has one vote. Every atom has a contribution to the pressure, which is kBT divided by volume. Every atom on the same basis as every other. Notice also that this result is the pressure is proportional to number of particles divided by volume, which means pressure is the same everywhere. It's property of density. So if you are looking at the piece of a gas, there is already density, and therefore you don't need to know how big is the volume, total volume of your gas. This is your pressure. It is determined locally. This is because it's density, it's local property. So if you look at this formula, you learn a lot. Indeed, as I told you, this pressure is due to thermal motion of the molecules, and these molecules you actually can derive, and probably most of you have seen derivation of this ideal gas law based on how molecules collide and transfer momentum to the wall. This derivation is nice, but a little confusing because it suggests that pressure is how molecules hit the wall, right? But then you may ask, well, wait a second, then it should depend on the properties of the wall, whether the wall is straight or maybe corrugated or maybe who knows what, or maybe the wall is soft. And no, pressure does not depend on that. And in order to see that, one way is to rederive ideal gas law, not from this kinetic, mechanical point of view, but thermodynamically. Compute free energy, you know this machinery. Compute partition sum, free energy, differentiate, blah, blah, blah. You all learned how to do it. And indeed, you can compute this free energy, you can differentiate, you rediscover ideal gas law, but you discover a few other features. First of all, you discover that indeed ideal gas pressure is due to entropy. It's not due to energy, but it is due to entropy. Okay, so because it's a property of thermal motion proportional to kT, it is actually due to entropy, entropic part of the free energy. Also, you learn that indeed it does not depend on the properties of the wall, which is consistent with the fact that it's a local property. And why it is independent of the properties of the wall, you can easily understand if you imagine that there is a pressure of this air on this wall, then this layer of air between this part and imaginary plane here, this piece of air must be in equilibrium. So forces on both sides must be the same, must be in balance, and therefore pressure here must be the same as at the wall. So I'm telling you things which are well known to you, well understood by you, but it's a reminder, and my experience actually teaches me that the better you understand elementary things, the further you can go. And the best thing is... Oh. Which one?
So for the S and the factor in the law, what is the E?
What is the E? Oh, E is 2.7. I don't know how do you call this number. Euler constant. Okay, Euler constant. All right. Euler constant. Euler was very, very remarkable man. I like the story about Euler that when he was old, he suffered from insomnia. In the day, he had some secretary who was helping him, but at night he was suffering. He was lying in bed and he was blind and could not do anything. So he had to invent some entertainment for himself. And what he decided to do, he decided to compute inside his mind, without any paper or anything, because he was blind, compute further digits of pi. 3.14, everybody knows, but then there are many. And he was doing it by summing some series in his mind. And in the morning, he would dictate the results to his secretary, but next night he would compute next digits and so on and so forth. And he computed some unbelievable number of digits, like 250 digits or something like that. And nobody, I repeat, nobody was able to check it until the era of computers. And Euler was right. All his calculations were correct. So
That's the reason why he get insomnia.
it's possible. But this is...
EV looks as if it could be the potential energy of an electron in a potential difference. I think that's the sad.
I agree, but this is Euler constant, so I'm glad to learn that this is called Euler constant. Never knew it. Okay, so closer to the soft matter situation, ideal gas is not really, it's very instructive, but it's not really close. So osmotic ideal gas is a bit closer to soft matter situation. So what is osmotic pressure and osmotic ideal gas? Osmotic ideal gas, the key for osmotic pressure concept is a semi-permeable membrane. So you should imagine that you have two parts of your volume. In one part you have, let's say, pure water. I will be, instead of saying solvent is a bulky word, I will use water, but it works for any liquid. So in one part it's pure water, in the other part you have some particles dissolved there, and the key is this semi-permeable membrane. It is permeable. Water goes back and forth without any problems. And particles don't go. I illustrate this here by these cylinders through which these big particles, these, let's say, pasta particles, spaghetti particles, cannot go through cylinder while water goes back and forth freely. So then you should imagine that, in fact, this volume surrounded by this wall, surface of water, this wall, and semi-permeable membrane is a balloon. So you really should master the idea that you should close the eyes on water. Water is there. You know that it occupies volume, but you should close the eyes. And you should think about it as ideal or maybe slightly non-ideal separate issue, but you can, for now, just ideal gas of these dissolved particles, of these big red particles. Ideal gas, and this gas exerts pressure and inflates this balloon, which is why water level here is higher. So there is inflation, there is the pressure. How do we, let's be a little more accurate here, and let's derive this ideal gas law. It's important to understand how you derive ideal gas law in such a situation. So you start from the fact that water goes back and forth through this membrane freely. So chemical potential of water in solution on this side, it is actually solution in which water is the dominant component, of course. And there is small component of these dissolved particles. And chemical potential, as you remember, is a function of pressure and concentration, number of particles, concentration. Concentration C of these dissolved particles. And pressure here is higher because of this balloon effect. Pressure in this part is higher, so it's outside pressure plus some extra stuff. And it is equal to chemical potential pure water here. Chemical potentials are equal because water particles can freely go through this membrane. So key is semi-permeable membrane. So you know that chemical potential of dominant component in water in solution would be chemical potential of pure water at the same pressure minus this little part, which is proportional to small concentration of dissolved particles and the volume per water molecule in just as a coefficient, and KBT, of course. And then this chemical potential of pure water, you expand, you do this Taylor expansion in this little additional pressure. Big pi comes in here, and chemical potential of pure water disappears, and here we are. And this is also called Van Gogh's law. Van Gogh discovered it about 100 years, actually more than 100 years ago, and received the Nobel Prize for this. Imagine 3 equations written now in every textbook, and the Nobel Prize was easy time. It was easy to. Okay, so this is just the derivation. This is an ideal gas law, and basic idea is that chemical potential is equal on both sides. Now I challenge you, and I emphasize that this is challenge not only for students but for professors as well. So we know that ideal gas law of real ideal gas, where molecules move in straight line, hit walls and get reflected, deliver momentum to the wall, you can derive this ideal gas law kinetically by counting how many molecules at which speed they move and so on. Now your dissolved particles, they move like Brownian particles. They don't deliver, well, what is the momentum of a particle moving as a Brownian particle? It's not very easy. There is some momentum, but it's not very trivial to understand what. And so the challenge is to rederive this Van Gogh's law from kinetic consideration of particles that don't fly like ballistic motion. They undergo a Brownian motion. I will not reveal the solution to this, but it's a challenge. Osmotic pressure is everywhere. This is the picture from somewhere on the internet about how osmotic pressure inflates and deflates red blood cells. Here is another picture. Many of the participants can remember using these devices, or maybe some participants can remember their children using these devices. And these devices are actually based on osmotic pressure. Or, as I will explain in details in one of my subsequent lectures, the way this thing works is it is a balloon with osmotic pressure of ions, and these ions inflate the balloon, osmotic pressure. So kids use osmotic pressure, although most of them don't know it. Okay, so this is the first part of my story about why soft matter is soft, and the summary. Soft matter is soft because of KT, generally speaking, because of thermal motion. Soft matter is soft because entropy is of great importance. Or you can say the other way around. Entropy is so important because it is soft. Chicken and egg. And soft matter soft because characteristic length, A, is actually much larger than atomic length. So for instance, I told you the thickness of DNA is 2 nanometers. It's small thickness in soft matter world, small distance, 2 nanometers, but it's 20 atom sizes. So it's already significant distance by atomic, and therefore KT divided by A, which is the force. This force is small, and this smallness of the force means softness of the material. Okay, any questions on this part? Don't tell me you understand everything. It's impossible. I don't understand many things in this part. Okay.
Are you saying that the entire softness of soft matter is coming from entropy, or is that this is one of the components?
This is what?
Are you saying that the entire softness of soft matter comes because of entropy, or this is only one of the ingredients?
Well, of course, it is one of the ingredients, but I would say that in general, entropy is a dominant force, dominant contribution to free energy is a general feature in one way or another. Of course, eventually there is competition between entropy and energy, entropy and enthalpy, and so on and so forth, but remember when I explained the hardness of hard matter, there was no entropy involved at all. It's purely an energetic issue. And now you are talking about the materials in which entropy, and entropy is infinite, it appears in infinite variety of different disguises. So you have to learn how to see entropy where it's not immediately obvious. So I can give you a hint. When you don't understand something in one of the subsequent lectures, don't use this trick with me, but with some other lecturers. Ask them, where is entropy here? This is a win-win. Yes?
Maybe a question about the fact that with this definition, granular materials, which is often considered as part of soft matter physics.
Which material?
Granular materials.
Granular materials, yes.
Out.
Yes.
Where's the entropy, sure?
I said don't do this trick with me.
I agree, but it was just to be That's what he's really
I entirely agree with you. First of all, I never really understand why the granular material is a soft matter. Second of all, I really don't understand where is entropy there. And third of all, I strongly suspect that the real problem of granular material is to understand where is entropy there and what plays the entropy, where is the role of entropy there. As you know, for instance, Sam Edwards, had a special series saying that logarithm of available volume is. So maybe it is it.
So going to push on a mildly philosophical point, but of course there are two views of entropy. That entropy is structural or epistemological.
Okay.
So the point is that if I look too hard, so if I do a molecular dynamic simulation in my brain of everything I know, all the degrees of freedom and everything, there's no entropy in my model whatever.
I know, of course, entropy comes. First of all, entropy, between you and me, I suspect that entropy is not fully understood as a concept.
I think that's true. So, I mean, the point is, if entropy is epistemological, i.e. it describes my ignorance of my model of the world rather than the moral world, then there is no problem applying entropy to a sample.
Well, I agree, but if we want to be a little more mathematical, and at least I want to be a little more mathematical, then I want to know how to use entropy in something more than just words. I want to compute something about sand pile.
Which is what Sam was trying to do.
Exactly, yes. Okay, so should we go on? Oh, yes, please.
Could you maybe elaborate a little more on why entropy is soft? Is it intrinsically soft? I'm not sure I understand fully that sentence.
Oh, you mean this green sentence? I was trying to understand. I see. So it's probably clumsy English here. Entropy is important because it is soft. I did not mean that entropy is soft. It should be read as a continuation of this blue sentence. Soft matter is soft because entropy is of great importance for soft matter. For soft material is soft if for this material entropy is very important. Or alternatively, you can say entropy is important for a particular material because this material is soft. Softness of material suggests to you that entropy is important for this material.
Okay, thank you.
But sure, can I say one more sentence? I think it does mean something. Because you only get entropy when you coarse grain.
Exactly.
So in a sense, coarse graining therefore gives you a length scale which is automatically larger by at least one order of magnitude than the atomistic, which in order to have entropy, and then you start dividing KT by that length scale.
Yes.
So that, I think there is a sense in which that green sentence says exactly what it means, or means what it says.
Okay. Maybe you are reading my mind when... Yes.
I don't understand why entropy is not important in hard materials, because if we go at the atomic level, if we look at the electrons and protons, then entropy might play a role. I'm not sure.
Absolutely, it does play a role. No, I'm not saying that when there is some solid state summer school in this auditorium, they neglect entropy from day one, as we neglect quantum mechanics and H bar. I'm not saying that. I'm saying that entropic effects are dominant, are leading in soft matter, while they are typically subleading in hard matter. This is exactly the point that I was trying to emphasize by juxtaposing this compressing a crystal in which one atom pushes on another atom to ideal gas. When you compress ideal gas and nobody pushes on anybody except the fact that you compress it, affects in some way how these chaotic motions develop. Okay? Should we continue? Wonderful, thank you. I like the fact that You guys are not sleeping and are participating. That's much better fun to teach in such situation. Okay, so polymers and ideal polymers. So when people say polymers, then at least in my experience, what people imagine are these plastic bags. And I think it's a wonderful picture of plastic bags. So they are made of polyethylene, and polyethylene is, if you ask chemists, chemists would say something like this or something like that. This is the image of polyethylene. Another polymer that maybe even more famous polymer that everybody knows is this, and I will not even comment because, of course, everybody have seen these pictures or similar pictures too. Another famous polymer. So this is a picture. This is a picture. And this is a picture of DNA. If you look at DNA under electron microscope, you never see this straight line. It's only on the picture that you see the straight line. What you see really is this thing. Well, here it's a ring DNA, which is because I just had handy the image with ring DNAs, but if you look at linear DNAs with free ends, same picture, it's wiggly. So if you take this polyethylene molecule, it also never straight zigzag like this. So why it's not straight zigzag? It is because, in fact, around this bond, you can do rotation. And since the bond is not collinear with the axis, so when you rotate around this bond, around this blue axis here, then this part of the molecule goes around the cone. And this can happen at every bond. So in the end of the day, this becomes wiggly. So the message of this discussion is that polymers are basically never straight, they never like this, but they form something that is called a coil, and they coil up in various ways. Fact of the matter is that different polymers bend, they all bend, but they bend in different ways. Okay, so those are two examples of the things that bend in fundamentally different ways. And DNA does not bend through this rotational isomer mechanism. This is called rotational isomerization. This rotation around the cone is rotational isomerization. DNA bends in a very different way. DNA is a double helix, so double helix, there are two chains, two covalent chains. You cannot simultaneously do this rotation in both, and therefore it has to do something else, and it deforms like a piece of wire. So DNA would bend more or less like this in smooth way, and other things bend by acquiring kinks everywhere in many places. So this is a little more details, and I will probably even skip this slide. It is a little more details about how a rotation around these single bonds, how this happens. And the only thing that I will tell you is that there is a whole machinery to describe these rotational isomers, how to describe all geometrical properties. It is quite difficult geometry when you imagine that you have this bond, rotation around this bond, and then next bond, rotation around this bond, and it starts spinning in your head how the whole space rotates around different directions. There is mathematical machinery. The best place that I know is the second book by Florik on conformations of chain molecules. There are ways to do it. It's quite automatic. So don't worry about it. If you need to understand anything about this, there is mathematical machinery to understand it. So that's okay. This thing, double helix, bends in a very different way. So it bends smoothly because you can think of it, you can think of a double helix as just an elastic rod, pretty much the same as, I don't know, for instance, there is somebody's glasses, and this is an elastic rod, and you can imagine that I can bend it. I do not plan to break it, but maybe there is a better rod somewhere. No. No rods. Okay, so, but you imagine what I have in mind. So mathematically speaking, you can think of it, you can imagine that there is a particle that moves along this trajectory, and S, which is actually a contour length along the polymer, is like a time in the motion of a particle. And then this particle has velocity, which is quote-unquote time derivative of its coordinate, its velocity, its tangent vector, and then bending energy is proportional to, so to speak, acceleration. It's how rapidly tangent vector turns around. Tangent vector is always has unit absolute value, and this is second derivative is how it turns. So the coefficient kappa here is due to the hardness of the material, how elastic is this rod, and you can actually derive it or just borrow it from a classical elasticity textbook. By the way, interestingly, I didn't even realize that when I told you about Euler story, I didn't realize it because this formula was derived by Euler, same Euler. I don't know whether he derived it at night while suffering from insomnia or maybe in the day, that I don't know, but this is the formula. And importantly here, notice that this is proportional to the force power of diameter of the rod. So it's very strong function of the diameter. For instance, now people do use DNA origami technology to make so-called 6 helices bundles of DNA. 6 double helical DNAs assemble into a bundle. So you can imagine that your diameter increases by a factor of 3. Not a big deal, factor of 3. But when you take 3 to the power 4, it becomes a very big deal. It's almost 100. So this 6 helix bundle is a very stiff object, super stiff object. Okay, so just elastic rod model. And this elasticity, when you place your DNA in solution, and it is bombarded by water molecules in KT fashion randomly from all directions, this elastic rod starts wiggling, and it exercises this formula and thinks, oh, Leonard Euler. Okay, so scales. I mentioned to you that KT is 4 piconewton time nanometer. Covalent bonds are very strong. And so covalent bonds for us, for soft matter polymer physics, covalent bonds are unbreakable bonds, period. Forget it, they don't break. It's of course exaggeration, they do, but okay. Bending, on the other hand, is much cheaper. either bending by isomerization or bending by smoothly deforming things like DNA, double helical DNA. This is much cheaper. And this is the place where our friend KT and our friend entropy, they start playing a role. They help us in exploring all the possible ways to bend and all the possible ways to coil. This is where entropy is coming. So monomer size, the size of 1 unit of the chain, is typically on the order of nanometer or fraction of a nanometer. Monomer mass is like this, but I will never use monomer mass. Polymerization degree, number of monomer units in the chain, changes in huge range, like this. 10 to the 9 is human genome type of thing. Human chromosome is on this order of magnitude. And contour length is from 10 nanometer to a meter, again, for DNA. So those are polymers, but I am supposed to tell you about ideal polymers. So why polymers are ideal? Some polymers are ideal because they are similar to ideal gas. What are ideal gas? How ideal gas is different from any other gas. Ideal gas is, of course, the invention of some theorists, and this is something that in pure form doesn't exist in nature. It is something where molecules fly in straight lines and never collide to one another. Just never collide to one another. I have to tell you that this is actually quite subtle. This is something that most of the students don't appreciate. This is very subtle concept, ideal gas. Why? Because if they really don't collide to one another, and walls are just plain walls, elastic walls, as textbooks present them, then how the hell these molecules know that they don't communicate to one another? How do they know that they have the same temperature? How do they establish Maxwell distribution of velocities? It's impossible. So really, ideal gas is a tricky, controversial approximation in which we assume that somehow they a little bit interact sufficient to establish thermodynamic equilibrium and Maxwell distribution of velocities, but then when it is established, then they interact weak enough such that over short period of time they almost do not collide. So it's tricky. But on the surface of things, it's okay. We just say they don't interact. They don't collide. So how about polymer? Polymer bends. I told you polymer bends. And if you bend, should I risk again these glasses? No. I will use my glasses. So if this object bends, it bends, these two parts can collide to one another. Okay? Parts of the rod that bend can actually collide to one another. They can touch. When they touch, as any material objects, they start interacting. There are some, if nothing else, if they really touch, they are physical bodies. They have some volume. I touch this, I interact with it. There is some force. So when this collision happens, there is some interaction. There is some force. There is something. Among other things, remember, I told you you should forget that this all lives in liquid, in water. So this white stuff is really liquid. So when they come close, they actually push water away from this. So therefore, there are some forces due to the fact that there is solvent. So the concept of ideal polymer is to say, oh, Nothing. They do not interact. They just, no, we neglect it. We just completely neglect it. Ideal gas comes in many varieties. You can have a gas of single atoms, gas of molecules, 2-atom molecules, 3-atom, 5, 10 atoms molecules, and so on. And they are all ideal if the molecules do not collide, do not interact. Similarly, ideal polymer can come in different varieties based on rotational isomers, based on elastic rod model, based on anything else. They are all ideal as long as we can neglect this interaction. In polymers, actually, the range, the situations in which ideal polymer approximation is a good approximation to work for real objects is wider than for ideal gas. The concept of ideal polymer is more widely applicable than ideal gas, for the reasons that you will learn mostly in subsequent lectures, such as surprisingly in the melt when there is no solvent and everything is packed with polymers. You would say, for instance, if you imagine all volume is packed with atoms, this does not look like ideal gas at all. It is already a crystal. Surprisingly, when the all volume is packed with polymers, every polymer behaves like it is ideal, for the reason that somebody will explain to you later. But it's a fact. And there are some other circumstances. So it's a useful approximation to imagine that polymer is ideal. But again, ideal polymers come in in many different varieties. And here are some examples. You can have ideal linear polymer. You can connect ends and have ideal ring polymer. You can have ideal branched polymer of this type, or this type, or this type, or you can make a whole network of ideal polymers. So you can make everything. There is you can make also homopolymer, which consists of all monomers of the same type, or heteropolymer that consists of different types of units. All of them can be ideal. I'm afraid I'm losing the microphone, but let's worry about it when when it's lost. There is a controversy, though, about structures like this when polymer makes a knot. Because if it's strictly ideal, then it should be, as people call it, phantom, in the sense that two pieces of polymer can go through one another like phantom, not noticing each other. Then this object will be the same as this one. But you can imagine also slightly less purist definition of an ideal polymer in which they do not interact all the way until they approach zero distance to one another, but at zero distance they still cannot cross. Then this object and this object and this object are all interesting separate objects. So different people use different terminology about it, and I will not go into this, but this is just for you to know. So ideal polymer, it coils. So for instance, idealized concept of ideal polymer with rotational isomer mechanism of flexibility would be this so-called freely jointed chain of rigid segments that are connected by joints in which they can absolutely freely rotate. And then you can ask how far does it coil. So its contour length, its total distance between one end and the other end measured along the backbone would be proportional to the number of these sticks, number of sticks times the length of one stick. But it coils, so in space it takes less volume, occupies less space, and you can find what is the typical end-to-end, for instance, distance of this object. So you can find it mathematically very easily if you say that this end-to-end vector is the sum of bond vectors here. Every bond is a vector, and you make a sum of all these bond vectors. You obtain this formula, and average, of course, average of this vector is 0, because as likely as it points this way, it points also this way, and therefore on average it is 0. But of course, average absolute value is not 0. And in order to find absolute average absolute value, what you easier think is to find square of this vector. You square it, and you realize that the cross dot product of different bond vectors is 0, because they rotate absolutely freely. And therefore, this is simply this cosine is 0 except when I equals j, and therefore you obtain this formula, very beautiful formula. R squared is n L squared, where n is the number of these sticks and L is the length of one stick.
There is a question up there that I see. What's the average over? Is it over time or over configurations?
Oh, that's a very good question. It is, you can think of it either way, and the result is the same as always in statistical mechanics.
Or over many polymers in your field of view?
Yes, you can average it over ensemble of polymers, over ensemble of different realizations of the same polymer, or you just watch your polymer moving in water and fluctuating in water and averaging over time. The result will still be the same.
Thanks.
Okay, so you can do it in slightly more general way. If you imagine that there is some the correlation between neighboring vectors is not exactly absent, so the joints are slightly non-perfect, then there is the same formula, n L squared for this mean square distance, n L squared, but there is also a coefficient here. Well, coefficient of order 1, so I will probably skip this story. It's a little boring story. So you can compute it. That's okay. If the joints are not perfect, then there is a little coefficient. Okay. But I want to concentrate on this. R, so we decided with you that n L squared was the estimate for mean square distance. And so R, typical absolute value of end-to-end distance, is proportional to the number of segments to the power 1/2. And for today, it's probably not a quite stupid idea, but it came to me yesterday that actually, as you know, Napoleon Bonaparte was born on this island in the town of Ajaccio, which is why airport is named under his name. And Napoleon, in general, in history textbook, he is presented as general, warrior, and so on and so forth. In various countries, of course, he represented in different ways. In the textbooks that I was taught on in Soviet Union, he was represented as unsuccessful conqueror of Moscow. So whatever his historical role, the fact of the matter is that he was a big enthusiast and supporter of science in general and mathematics in particular. In particular, he loved and supported Laplace. So every time that you use Laplace equation, this is partly due to Napoleon. So you will see later that this square root is related to Laplace equation. So therefore, I decided for today to call it Napoleon principle. So this is Napoleon principle. In more details, you can write it like this: bond length, which is L in previous slide and B in this slide, but N to the 1/2 all the time. You can rewrite it as B times contour length to the power 1/2. So let's, and those are mathematical computer simulation of this thing. And this is actually similar to random walk. If you remembered your physics textbook about random walk, this is very similar to the random walk. This is basically the same thing. So how about not these rotational isomers, which are simplified to mean freely jointed chain? How about this elastic rod model? Elastic rod is something different, right? It bends smoothly. I told you about this. So how about this? In this case, instead of the sum of the bond vectors, what you can have, instead of the sum, you have an integral. Instead of the bond vector, you have this analog of velocity. So this is similar formula. And then, based on this formula, you can actually go through some mathematics, which is fully written here, so it's not very difficult mathematics at all. And you can derive for your R square, mean square, end-to-end distance of this elastic rod model polymer chain. You can derive this beautiful formula. So let's look at this beautiful formula. Let's concentrate. I will skip the mathematical derivation of it. If anyone is interested, please, maybe we can do it on the board after the class or anytime. Ask me, I can show it to you. I just want to do something more exciting. So let's look at this formula. Big L here is total contour length of this wiggly, smooth, wiggling, bending, smooth rod. Let's call it DNA to be specific. Big L is this. Little L, okay, we will see what is little L. It is a parameter that is related to how stiff the rod is. And let's look at this formula. Whenever you look at formula, by the way, you should acquire this habit. If you look at the formula, think of what happens to this formula in various simple limits. So in this case, there are obviously two simple limits. When two lengths, big L and little l, this quantity may be large compared to unity or small compared to unity. If it's large compared to unity, then this is large, and one you can neglect, and the exponential you can neglect, and you obtain this. If, on the other hand, this quantity is small compared to unity, then you have to work a bit harder. You have to expand your exponential in Taylor series. Taylor series, I hope you remember what is Taylor series. In New York, when I teach in New York, I suggest people to go to Fifth Avenue. There is Lord Taylor store, and I tell them that they have Taylor series on sale. And so Taylor expansion, you have to keep three terms that you obtain big L squared. So let's understand what that means. So this limit, when total contour length is small compared to this so far not perfectly defined length little l, then this is basically L squared, which means that this rod is basically straight. Distance between ends is basically the same as just contour length. It's a straight rod. Almost doesn't matter. In the other case, however, this formula is exactly like the Napoleon principle. It looks exactly like control length L times little l square root. It is exactly the formula that I presented here. So it is Napoleon principle. So even in this case, in this smoothly bending object, we recover this square root Napoleon. For now, for today, I call it Napoleon principle. Since we are in Corsica, we should show respect for everything Corsican, and let's call it Napoleon principle. So this is Napoleon principle. That means this little l, or rather 2l, this 2l, plays the role of effective segment. It's called effective or Kuhn segment because this smoothly bending object can be presented as this random walk-sync with effective segment size to be this 2 little l. So now it's time to remember to say what is really this little l. It turns out that, it turns out that average cosine of the angle between, let's say, this tangent and this tangent, if they are in points S and T along your chain, average cosine of the angle exponentially decays with the distance between points. And this is characteristic length of average of this decay. It's called persistence length. It tells you how your road persists if you put it in this direction, how it persists to keep this direction. It persists for distance of the order of the persistence length. Persistence length is the important characteristic of every molecule. Persistence length of double helical DNA is 50 nanometers. You may want to remember 50 nanometers. If somebody wakes you up at 4 o'clock in the morning, as I woke up this morning, I immediately thought, oh, persistence length of double helical DNA is 50 nanometers. You should acquire the same. Okay, so persistence length is correlation length of these directions, and 2L is effective segment or Kuhn segment. Those are just words, and they are summarized in this slide. I think I told you everything already. So effective segment is 2 persistence lengths. The number of segments is contour length divided by this 2L. So on large scale, everything obeys this Napoleon principle of square root of L. Okay, so now maybe it's time to look at it from a different point of view. And let's ask how many molecules, how many monomer units you have if you encircle a sphere of radius r, how many monomers would be inside this sphere. So you just reverse your Napoleon principle formula, and you obtain that the number of units inside there, inside R, is this. So it's another form of Napoleon principle. So this 2 that is written red here is actually, it has another pompous name. It's called fractal dimension. So the statement is that this ideal polymer on large length scale is an object with fractal dimension 2. I do not plan to explain it in any details. My understanding is you will hear about it later, because other polymeric systems have different fractal dimensions. Some of them have smaller, larger fractal dimension, and so on. This ideal polymer has fractal dimension 2. which roughly you can understand if you imagine that you place your ideal polymer on the plane, just squeeze it on the plane. On the plane, it will more or less cover it uniformly. So on the plane, it's uniform. So it's, in this sense, it's two-dimensional. But I hope that somebody will explain it to you in greater detail. Now, so far, we discussed with you end-to-end distance of the coil. And end-to-end distance is a useful thing. The Napoleon principle tells you that this is square root of n, which means it is much shorter than n. For long polymer, fully stretched will have length n. Let's imagine that n is, I don't know, 10 to the 8. So 10 to the 8 will be this. And now you take square root of 8, it's 10 to the 4, it will be like this. So really, instead of straight object, it coils up and becomes much more compact. But how do you know really how compact it is? Because, one second, I will finish the sentence. This r is actually the distance between ends. So maybe two ends come close to one another, but the whole loop is very big. So in order to be more careful about intuitive idea about how big is the object, there is a quantity called gyration radius.
This is the question.
Good. This is super. So when a student asks a question and you are able to say, oh, this is exactly what I'm going to say, this is very good. So the gyration radius is defined. And gyration radius is also useful because it is something that is directly measured by, let's say, elastic light scattering or neutron scattering or something. So this quantity is defined the following way. If Ri is the position vector of monomer number I, and RCM is the position vector of the center of mass, and you measure distance from monomer number I to the center of mass, take the square, and take average for all units. Now it turns out that, this is center mass. It turns out that you can actually rewrite this definition of gyration radius in different form. Instead of having center of mass, you just take average distance from monomer number I to monomer number J. Every pair, and you see you sum over both I and J, every pair. This is computationally usually easier to do it like this. And surprisingly to me, this statement was proven by nobody else but Lagrange. I do not know in which context. Why Lagrange was thinking about it, I don't know. But this is just a matter of simple algebra. So for ideal polymer, where R square is NB square, so gyration radius square is NB square divided by 6. So 6 is a useful thing to remember. It's quite easy to derive. It's just 6. Okay, so how about doing this? I'm a bit late, but I will manage to do it. I will manage well. So actually we can check all these observations by experiment. And the beautiful experiment that was pioneered by Bustamante, Carlos Bustamante, not so long ago on my time scale, but perhaps very long ago on your time scale. I was like 25 years ago. So he managed to take DNA chain, to attach one end to optical or magnetic tweezer, and then exert force. By the way, this picture is actually not right in terms of scales. If this orange thing is the DNA, then this blue thing should be about as big as me. Not like this. So it's a really big thing. But it doesn't matter. So you apply the force, and you pull by force, and you measure extension. So really, R that we so far just computed R to understand that there is this coiling up, and this was very easy. This R is a dynamical thing. You can exert force and explore how this distance responds to the force. So why it is related to the equations that we discussed is the following. Let's remember that end-to-end, maybe I'll show it to you. Let's remember that this vector R is actually the sum of these bond vectors. Every bond vector is randomly oriented, and this R is the sum of many independent random variables. You probably know from some mathematics or probability course that when you have a sum of many random variables, then the distribution, probability distribution of this sum is Gaussian. So, indeed, you can show that this probability distribution is given by this formula. It's proportional to this exponential. I provide here some derivation of it, but I am running out of time, so I'll skip it. I just refer it to central limit theorem, which says that it is this formula. But you can reinterpret this differently. You can say, probability in statistical mechanics is exponential of minus free energy divided by kT. It's exponential minus free energy divided by kT. So you can take the log of this and find the free energy. You can say that this kBT R squared divided by this Napoleonian NB squared is free energy. Okay, so it is the free energy. You can now imagine that you hold your tweezers at distance r from one another, and that means you fix free energy. When you are talking the ideal gas, you have a piston, you hold the piston, and you have some free energy of the ideal gas. And instead of holding the piston with given volume for ideal gas, you hold the tweezers for ideal polymer, and you have free energy of ideal polymer. The more you pull, the less freedom your polymer has, the less entropy it has, the bigger free energy it is, the more free energetically unfavorable it is, and so on. This is given by this formula. Okay? So if this is the formula, then you can, of course, derive the force, because force will be derivative of free energy with respect to distance, and so the force will be like this. Force proportional to R, and this is, you can say that this is elasticity constant of your polymer. And how beautiful it is. Elasticity constant is proportional to kBT, Remember ideal gas pressure proportional to kBt. This thing is also proportional to kBt. For exact same reason, it's all entropy. It's entropic force. It's not due to energy, due to collision of atoms. It is due to the fact that you reduce, when you pull, you iron out wiggles. The more you pull, the more iron away the wiggles. And indeed, if you pull and you change R, the force shoots up. The beauty of this experiment is it showed actually that this is not described by freely jointed chain, which is this line. The points well approximate the worm-like elastic rod bending model, which is the model for DNA, and this is, but in terms of qualitative fact that I am concentrating on now, it's not so important. The important thing is that the force shoots up, because the more you pull, the more you iron out. You work very hard to suppress, to remove any possibilities of fluctuations. You work against freedom. You are a fighter against freedom. You are doing bad thing. You have a question.
I did not completely follow. What is the difference between freely jointed and worm-like?
Between what and what?
Freely jointed and worm-like.
Oh, freely jointed is freely jointed. Yes, it is freely jointed. Worm-like is the same as elastic band model, elastic rod model. Elastic rod model that I described to you, where flexibility is controlled by Euler formula, and there is a rigidity coefficient proportional to force power of the thickness. This is worm-like chain model. So this result means that double helical DNA is better described by it's actually very well described by the elastic rod model. It's not so well described by the freely jointed chain model.
Sorry. So in the worm-like model, we have this persistence band, right?
Yes?
So, and on the scale of the persistence band, does it not lie? Like between two, it's like a rigid bar on the...
Yes, so you ask, why the hell, when they look so much similar on large scale, why at this stretching they look so different? The answer is a very good question, and the answer is the following. When you pull, what you do is you iron away fluctuations. Which kind of fluctuations you iron away? If you iron away large-scale fluctuations, which you can think of effective segments is almost relatively, then you are here, and in this region, these curves are almost the same. But when you pull very strongly, you actually start to iron away fluctuations which happen on smaller scale. You start to work on freedom. You see, when you, in political world, where you start fighting freedom, you first close, I don't know, television stations. You close newspapers. Then you work harder and you start, if you remember Orwell, you start listening to what people say to one another in their kitchens. Then you mount microphones under their blankets and ask and listen what they say to each other in bed. And this is similar here. You pull and pull and pull, and it's strong force. It's about 100 piconewton force. No, sorry, it's about several piconewton force. It's force divided by, so it's very strong force. So you work very hard and you iron away fluctuations on small scale.
This irony away of political freedom,
Yeah. Yes.
otherwise the Cargese people would be
Yeah, absolutely. Okay, so this is my summary of ideal chains. So this is Napoleon principle, gyration radius, Gaussian distribution, free energy, and force proportional to R. This is all you need to remember in order to feel comfortable in next lectures. Thank you.